Great. So what we did last time, we figured out what happens when you shift around interval rank varieties if you choose the right shifts. And I want to connect that to puzzles. So before my puzzle pieces, so the puzzle pieces were this triangle with zeros on it, this triangle with ones on it, and this triangle with ones and zeros. This is sorry, it's not a triangle, it's two triangles put together like that. And you're allowed to rotate them. But and the whole puzzle was something like 0, 1, 0, 0, 1, 0, 0. So when one looks at this, by the way, so just on things to figure out when filling in puzzles, if you have a 0 and a 0, the only way to fill that in is like that. If you have a 1 and a 1, the only way to fill that in, similarly with ones. If you have a 0 and a 1, the only way to fill that in is with the rhombus. If you have a 1 and a 0, then there's finally a choice. You could either put a 1 there, and then have to have a rhombus, or you could put a 0 there, and have to have a rhombus the other way. So looking at this, I say 0, 1. So if I say 1, 0, oh, there's a choice. But if I make the wrong choice, I'll get screwed up later. So I look here and say, oh, there's no choice. And I could either do it this side or that side, make forced either way. All right. And what this is saying is I'm in the Grassmannian of 1 planes in 3 space, which is to say points in the projective plane. That's because I've got 1, 1, and 2 zeros. So I've got points in the plane. This condition says that my points lie on a line. This condition says my points lie on a line. And if I ask, what happens when I ask for a point to be on a line and another line? Well, it has to be the point of the intersection. So that's what it says that this was the unique filling of this. All right. So that's where things were. But now I'm going to be relating that with this study of upper triangular matrices. And so maybe let me label this north and southwest and southeast. Those corners are going to get twisted around like this, north and southwest up here and southeast down there, in order to compare to these partial permutations or these rank matrices. So remember that I was filling these in, zoop, 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 according to this Vauquel degeneration order, and at any given time, there would be some particular square AB that I'd be thinking about shifting A to B. If I take one of these puzzles and I move it over to there and I cut it like that, there's the possibility I might cut a rhombus in half. So my puzzle pieces are now going to change a little bit, so let me not worry about the shape right here, but there's going to be this one and this one, and now there's going to be this one, R is for rhombus. So all I did is I cut this puzzle piece in half, and I could have actually set up the whole original theory of puzzles with those 3 puzzle pieces instead. So those guys and rotations, but then I need to be explicit. No R's on the boundary. So this is my new definition, very, very, very equivalent definition of puzzle. It's something made out of these 3 kinds of pieces into a big triangle like this, and it's not allowed to have an R on the boundary. And the reason it's equivalent is any R you have in the middle somewhere is going to have to be on 2 of these, one here and one the other way, and they'll fit together into an old rhombus. So it's just the same as the old theory. But I need to talk about it this way because I'm going to be cutting pieces in half sometimes. So what I want is, given puzzle labels on this part of my puzzle, and this is going to be at, this is in row A, column B. Associate and AB partial permutation. So for each puzzle, there will be a partial permutation, not puzzle, but for each sort of partially filled puzzle. And you could say that I should have puzzle pieces down here, but I'm actually not going to use them to define this. I'm only going to care about what the labels are. So for each partially filled puzzle, or just labels on it, I'm going to associate a partial permutation, and therefore a subvariety of the Grassmannian. And then the statement is going to be that shifting the subvariety, and possibly breaking it up, is equivalent to filling in 2 more triangles in the puzzle. Because that square, coming back to here, corresponds to 2 triangles. Okay. So, here's the rule. There's going to be, so the rule is different in the lower half and the upper half. The upper half is really the interesting part, the lower half. Because remember, the upper half eventually is supposed to have some dots that are going northwest to southeast. And the lower half is supposed to have some dots that are going northwest to southeast, but they have to be in the top rows. So there's more going on in the upper half. There's more freedom. And that's where I'm going to focus attention first. So there's going to be zeros here, and zeros and ones. Zeros, ones, okay. And there's going to be zeros and ones here. I'm not going to be careful about how many there are of things. There's going to be zeros and ones, but along here there can be zeros and ones and r's, and also this thing I call the kink, and there's going to be zeros and ones and r's in this part too. And the rule is, so I'm going to draw rays, so a ray is something like that, and I'll make them red. That for each zero on the right, there should be a ray like this. For each zero on the left side, there should be a ray like that. For each R on the bottom, there should be a ray like that. So these rays, so this is in the upper half. Ray like that. Then there's this tricky bit. If the kink is a cut rhombus, then it gets a ray, and the next one to the left gets a ray also. So mostly I've got these rays coming up from zeros and from r's and coming right from zeros. But I might also have there might be one ray coming up from a 1. So let's say that with all that done, I end up with 3 rays coming this way and 3 rays coming that way. Okay. So I could look at all 9 intersections of these 3 with those 3. And I would get this sort of 3 by 3 matrix worth of intersections. That's where I'm going to put dots. But I know that I want the dots to be northwest to southeast. So I only bother connecting these so they don't cross each other. And put the dots there, northwest to southeast. So put the dots at the intersections of the rays, northwest to southeast. I should step back and say something philosophical here about what parts of this I consider important for you to understand, what parts I don't. So I think the geometric shifting idea that's really pioneered, and to my knowledge, in Robbie McHill's paper is great for studying subvarieties of flag manifolds, in particular studying T invariant subvarieties. And I think it's really interesting how it's connected to combinatorial shifting. I wish I had time to tell you more about that. And I think puzzles are great. I really do. And that's why, when invited to speak here, I said, I'm going to talk about puzzles of the many different aspects of Schubert calculus. So that's a personal opinion. I think it's delightful that one can connect the shifting to the puzzles in such a way that everything along the way means something geometric. And actually the things that it means are these interval rank varieties, and I think they're pretty nice too. That said, I'm not sure that all the details of this are so important for every Schubert calculator to know. I mean, I'm telling you them to say, yes, one can make it precise, but that part of the puzzle goes in, and there's a way of associating, so that there's a way of doing this. But the actual details, I don't think there's any more. Yeah? Right, so that's not automatic. If I just put arbitrary labels along here, then this would not happen. So I'm not going to be putting arbitrary labels on there. So thank you, I wanted to say that. If the number of rays this way, red, if the number of rays this way versus this way are unequal, then the labeling is bad. And we shouldn't associate, or shouldn't make a pie. So let's think about the very first case of this. What if I have the square all the way down here, and what the path looks like is just that? Then I'm saying, if you're trying to fill in a puzzle where you've got a different number of zeros here and there, then what are you doing? What dimension Grassmannian are you on? So at the very beginning, we're only going to be interested in this if we've picked what the dimension of our Grassmannian is, and we have the same number of zeros here as we do there.
So you're starting out with zeros on this diagonal and then on the third.
Yes, where the black is, right? It's only on the black is where. Ah, yes, very very important point. So recall that where that's, thank you, Matt, for bringing that up, right? So recall that C lambda mu nu has two sources. So we can either say I want to multiply x lambda by x mu, by x mu, and expand in nus. But the other way we could do it is we could say I want to expand x mu super nu in terms of x super lambdas. And the reason this is true, okay, I say recall, it's because it's something I meant to say on the first day and realized I didn't say. No, because I never did the duality of the basis and dual basis. So, and this is because, one, if you multiply one of these by one of those, and you integrate over the Grassmannian, you get the Kronecker delta. So this says that we have these two different bases for the homology of the Grassmannian, coming from Schubert varieties and from opposite Schubert varieties. And those two bases are dual bases under this Poincare pairing. So I didn't say it before. What I said was that this basis was the same as that basis, re-indexed. So it's the basis is dual to itself, but you have to re-index. You have to by the W naught. It's not an orthonormal basis. So I didn't prove this, but I'm not going to now. You can think about what I'm doing here is thinking about the intersection of this Schubert variety with this opposite Schubert variety, and three things can happen. It can intersect in the empty set, that's fine. It can lambda and mu can be equal, and it intersects at a point, and we get the one we're looking for. And the last possibility is that it can intersect in something positive dimensional, and then you still get zero. So the only time when you get a point is when lambda, or even in a finite set, is when lambda equals mu. And what that implies is that you can think about C lambda mu nu as the integral of x lambda times x sub lambda times x sub mu times x super nu. So if you say dualize this, then you get x lambda times x mu expanded in x nus. That's what I said I was computing, but I'm not. I'm actually computing this, where I say, let's dualize the lambda side and have x mu times x sub mu times x super nu, so that, thinking about that Richardson variety from mu to nu, expanded in the duals to the x lambdas. So that's why there's an x super lambda. So this is really what the geometry is about. I start with the mu and the nu, and I degenerate using shifts to opposite Schubert varieties, and see how many times I get it done in various different opposite Schubert varieties. Thanks. Any questions right now? All right. So there's going to be some puzzle paths with labels on them that I will try and associate a variety to, and some that are just stupid that don't mean anything. And part of the condition of whether it's sensible to try and do it is that I should have the same number of rays each direction. Yeah?
So what you're saying is you start with a puzzle, and then you rotate, and then you cut it, and with that red rules you work with red, make sure that the number is vertical.
No, I'm saying if I had an actual puzzle, then that would all be automatic. So there's combinatorics there we're not going to do. But if there is honestly a puzzle, then this is no problem at all. What I'm saying instead is what's going to happen is if I have something that's good, and this is one of the goodness conditions, then after I put in two pieces and move and go around go the other way around the red box, that will again be good. So that requires a boring combinatorial proof, checking the as you see, not very many cases. So absolutely, I'm not going to tell you any of the case check going in there. It's, it was hard enough writing the paper. It's completely uninteresting. But I'll promise you that it works and that it's written down. You can find it on the archive. Where is it on the archive? There are 4 papers by anybody named Knutson with a puzzle at the title. They're online, and as yet. What I'm lecturing on is almost all the 3rd paper. I hope to talk a little bit about the 4th paper. Let's see. So that's what you do in the upper half, and in the lower. It's not as interesting because I don't need to say what rows things are happening in. They should happen in the top rows. So all I need to say is where the rays are going to come down from, and if the kink has a 1 on it, and there exists a 0 to the right, that 0, let's see, the 1 gets a ray, and of course there was that 0 that was getting a ray down, and those are going to meet at the dot. So what we'll have then is we'll have some rays, and maybe there's a ray coming horizontally here, but then put in enough rays here, zoop, 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 so that these can meet at dots. And you put them in the top rows because I want the dots to be as high up as possible.
So you'll of course get this what's the southeast range of paths, but you also have one in the road.
Yeah.
That's also one.
Yeah, it's okay to have one of that.
Okay. Sure.
So again, here's a recipe. Puzzle path with labels goes in, and assuming that this good thing is true, and there's another, that's it. Assuming that this good thing is true, then we can associate an interval rank variety. What you do then, you on the geometric side say, I'll apply this shift to that interval rank variety. And on the combinatorial side, you'll say, let's apply, fill in 2 triangles there. Put in 2 of these triangles. And the main thing I want to tell you, I think you know the punchline, but let me spell out one thing about it, which is theorem. If the labels at the kink are not a 1 followed by a 0, and I just erased the thing that said that's the ambiguous case where you don't know what to do, So if they're not the ambiguous case, then one, so, okay, let me call this labeled thing gamma, and this association, gamma goes in, and a partial permutation associated to gamma comes out. One, the variety defined by this is shift invariant. So that says that nothing's happening on the geometric side. You try and move it, and for every t, nothing happens. Take the limit, nothing happens. Take the sweep, nothing happens. So that's the geometric side. And the combinatorial side is there exists a unique filling of the red box that we're trying to fill, the one that's at position A, B. And once we filled it, we get some new puzzle path. So gamma went underneath the box, and gamma prime goes over the box. And it's got these two new labels there. And the permutation associated to gamma matches the permutation associated to gamma prime. So nothing had happened. So the puzzle has changed a little bit, but the permutation associated hasn't changed, which is good because the variety isn't supposed to have changed either. So this is, of course, the boring case. But we're almost always in the boring case. The only interesting case is 1 and 0 here, which was the ambiguous case I had before. So like the R's have not contributed any weird new ambiguous cases. So if the labels are the interesting case 1, 0, then on the geometric side, we find out that the variety is not shift invariant. And more specifically, the only way that this thing was not shift invariant was that right under here, there was an essential box in the diagram of pi gamma. And more specifically, when you shift it, so we already figured out in this AB Vakil case, we already figured out that when you shift this guy from A to B, that this was a union of 1 or 2 pieces. So we knew that. And these pi prime are the pi associated to each of the 1 or 2 gamma prime that you get by thinking about the 1 or 2 ways to fill this in. So I told you a moment ago that there were 2 ways to fill it in, but you may try and fill it in and run into a problem later. And there's a way of looking ahead and saying, at the end of this row, there's going to be something obstructing me from filling it in the bad way. So one of the ways is fine, and the other way would be bad. And so this is really the end of the statement that says filling in puzzles corresponds to shifting this Richardson variety until it breaks up into opposite Schubert varieties. And there's lots to check, but we've checked all the geometry. Not all of the combinatorics, but I feel I've told you the interesting and sort of generalizable bits that aren't so specific to mucking about inside the puzzle pieces. So what I want to go to now, I'm going to declare myself done in explaining the connection of puzzles to ordinary Schubert calculus. And what I want to do is talk about basics of K-theory and equivariant cohomology and see what's involved in what we have to further think about in the geometry to be sure we're doing those computations. Because actually, we've done all the geometry we need to understand K-theory and equivariant cohomology, so long as we understand what K-theory and equivariant cohomology are. So I want to discuss those from the basics. So, crash course in K-theory. So first, there's K-homology. K, lower bullet of A. A here is a commutative ring. And this is defined as we take the free abelian group on isomorphism classes M, finitely generated A modules. So, because I say finitely generated, there's some set of isomorphism classes. If I took all modules, then we'd be in, we'd have some set theoretic difficulties. And of course I would punt those, but actually I don't have to. There's a set of isomorphism classes of finitely generated modules. And I take a free abelian group on that great big set, and then I mod out by, I want the class of M2 to be declared to be the sum of the classes of M1 and M3 if there exists a short exact sequence. So, stupid case, M2 is the direct sum of M1 and M3. Then for sure there's a short exact sequence. So in particular, direct sums on the module side turn into ordinary sums on the K-theory side. But this is more general. There's plenty of short exact sequences that don't split, and I'm just splitting them effectively by the time I go to K-theory. And because it's an abelian group, I'm allowed to subtract. I can not just say, I know what adding modules means, and now I know what subtracting them means too. And everybody's favorite example is if you take a field, then all you're thinking about is up here is natural numbers, but because you take the free abelian group, is integers. So form the virtual dimension of a vector space. And this thing is a functor from commutative rings to abelian groups, except that if I have a ring homomorphism from A to B, and I have a finitely generated module over B, it becomes a module over A, but it might not be finitely generated. It'll only be finitely generated if B is a finitely generated module itself over A. So, and what are called finite maps of rings. So meaning A to B, B is supposed to be finitely generated over A. Then. So what kind of a functor is it? If I have a module over B, it becomes a module over A. So this is contravariant. So it's kind of funny that it's called homology and have a lower star. It's contravariant. So we fix that by saying, oh, we don't want to think about commutative rings. We want to think about affine schemes. So specs of those commutative rings. X to Y. And finite maps. And now this finiteness condition is the statement that this map should be proper with finite fibers. And now it's covariant to abelian groups. So I want to do an example of a calculation of one of these short exact sequences to see what this looks like. Let me first mention a theorem. So at this point, so this was defined in terms of these finitely generated modules over the ring. And now I'd have affine schemes, and the definition would now, in that language, would be K of my scheme is coherent sheaves on my scheme, so isomorphism classes of coherent sheaves, modulo short exact sequences. So that's just exactly the same statement as before, just using the geometric words to mean the same thing. There's no mathematics that went in and changing from that to that, just changing the language used. The only difference is now I know what those words mean on an arbitrary scheme. Some of you do too, I hope. That I can say coherent sheaf on a scheme instead of coherent sheaf on an affine scheme. And I'm going to do that. So theorem, if X has a cell decomposition, so disjoint union over some indexing set that I might call W, or something like that, or maybe W super P. Yeah, okay. Some indexing set I of a bunch of affine spaces. A, whatever. And I'll be careful. If X is proper, then the K homology has a basis consisting of the classes of the structure sheaves of the closures of those cells. So, of course, I'm going to be applying this to the Grassmannian. So you know exactly this statement in ordinary homology, in topological space. Topological spaces, and I'm saying this is something that says that K homology is like ordinary homology. Yeah.
Is X is affine or
No, X is not affine.
any solutions?
No. No. The cells are smooth because they're affine spaces, but the whole thing is not. So Schubert variety.
Oh, you can replace X with
X could be a Schubert variety, for example. Schubert varieties have the cell decomposition, and they have this property. Okay, so what's really nice about this definition is we can define G equivariant K homology. And what you do is you put a G on it. The scheme, and so where G is a group acting on the scheme. By the way, this is the way the arrow goes. So you don't have G, and then G, and then X, okay? So It's easy to avoid the ambiguity. So if you learn nothing else this week, I hope you'll take away this. I've got G acting on a space, and I'm going to define the G equivariant K-theory as I need to stick G equivariant sheaves on here. Coherent sheaves, classes of coherent sheaves, the Z module, whatever. But the main thing is that if I have a module over a ring, and I've got G acting on the ring and G acting on the module, I can talk about a G equivariant module, and I do that, I get this notion of G equivariant K theory. So it's extremely naive how you put the G in there, and when you do, you get the right answer. Spoiler, this is not true with equivariant cohomology. Equivariant cohomology is unpleasant to define. It's not you take definitions of cohomology and such and put G in them. And this is a sign, one of the signs in which K theory is better than cohomology, that it generalizes so easily to the equivariant situation. Okay, so now I'm going to give an example of an equation in G equivariant K theory. So let's think about X is going to be A2, and it's going to have T2 acting on it, scaling the two coordinates. So scaling this way and scaling that way. And so X is, this is when back in the affine situation, X is going to be spec of C bracket XY. So C2, if you like. Then I have the short exact sequence of modules. There's the module C bracket XY, because I'm going to call this thing A, so I'm going to keep writing it. There's going to be the module A bracket the ideal generated by X times Y. And you can further quotient this by X and by Y. And I'm going to do both. I'm going to quotient it by X, and I have a nice map from this onto that. But I've also got a map from this onto that, A mod Y. And this map is no longer onto. It has a co-kernel that's isomorphic to A mod X comma Y. And then it's short exact. So the corresponding statement on the scheme level is this is the structure sheaf of the origin. This is the structure sheaf of the y-axis where x equals 0. Here is the x-axis where y equals 0. And this is the structure sheaf of the axes. And so the equation we get in K, so everybody here is not just a module over A, but is a bi-graded module. So the T2 action here corresponds to the fact that this is a bi-graded ring. It's you can talk about the monomial x to the A, y to the b as having degree A comma b, and that's the bi-grading. And these are all bi-graded modules. I modded out bi-homogeneous ideals. So I'm going to get an equation in T2 equivariant K-homology of the plane. And what that equation says is if you add these up, you get that plus that. But I would rather write it as the class of this subscheme. Right? So I'm going to just write the class of y instead of the class of the structure sheaf of y. So I'm going to have this subscheme of the plane. This is living inside the plane. And I'm going to take its k-class, or really the k-class of its structure sheaf, and say that's the k-class of this axis. plus the k class of the other axis minus the k class of the origin. So as a combinatorialist, if you are one, you should like K-theory that it's keeping track of overcounting in a way that homology is not. Right? The homology statement is that the homology class of that is equal to the sum of the other two. But K-theory is more sensitive. It says, no, it's not. You're overcounting the origin, and it insists on it being there. So the correct statement is that there's a filtration of K-theory by the dimension of the support of a sheaf. You can say, well, I only want to think about the K classes that I can find some representative of that's supported on something very small. And if you take the associated graded, that has a natural map to homology. So I would say, here I've got this thing that's codimension 1, codimension 1, codimension 1, codimension 2. Well, in homology, you throw away things in lower codimension, higher codimension. And that's taking this associated graded. So what does that mean for Schubert calculus or puzzles? It means that when we have this situation where we degenerate one of these interval rank varieties and it breaks into two pieces, we can't just say the class of the original guy is the sum of the classes of those two pieces. We have to say it's the sum of the class of the two pieces minus the class of the intersection, just like I had there. And that means, so I made this statement that, remember this statement that if you have this bad thing inside your rank matrix, that you then break that up into either you shrink this or you shrink that. And now I'm saying, or both. So you should subtract off the case of shrinking both. So the way that's going to be implemented is with the K piece. I've got one more puzzle piece. Yes?
Because of the green structure.
Oh, thank you. So this was all K homology. So one thing you can do with sheaves is you can tensor them together and get more sheaves. And so you might think, therefore, I've got this tensor product on sheaves, isomorphism classes of sheaves, so I'll get a tensor product on this group, or a product structure on this group. The problem is that that multiplication structure you would try to define doesn't survive K equivalence. And the statement is that tensoring, it doesn't survive passing modding out exact sequence. The statement is that tensoring with a module is not exact. So if you want to make it exact, you have to work with nice modules for which tensoring with them is exact. And so the way that's done, K cohomology, K upper star of X, is the same definition, but now we take classes not of coherent sheaves, but of vector bundles. Of course, finite dimensional vector bundles, again, modulo short exact sequences. So if I take a sheaf and a vector bundle, I can tensor them and get myself a sheaf, and that makes K homology into a module over K cohomology, and that's analogous to cap product for ordinary cohomology acting on ordinary homology. There's always the one thing that's special to this situation is there's always the class of the structure sheaf of X as an element in K homology, and this is and this is a built-in fundamental class. So you might think, well, not every topological space is a fundamental class. Yeah, but we're dealing with algebraic varieties here, thinking of things over C, they're oriented because they're over C. So it's not unreasonable that in this algebraic situation, we get extra things we wouldn't have if we were just doing topology. Because we have a fundamental class, we could say, take that fundamental class, hit it with elements of K cohomology, and get a map from K cohomology to K homology. This Poincare map. And the theorem then is that if X is smooth and proper, this is an isomorphism. So here I've got this cap product. If I have a fundamental class, I can cap the fundamental class to get a Poincare map. And the statement is that's an isomorphism. So that's Poincare duality for K theory, which is so again, you think in usual topology that smoothness isn't enough. You also need things to be oriented. Well, they're sort of automatically oriented in this sense, because I'm doing things. If I'm trying to compare directly to topology, so I'm doing things over the complex numbers, then these spaces will be automatically oriented. So one thing about that, if I have a homology class here, if I have some sheaf, some coherent sheaf, then you could say I'd like to make I've got this finitely generated module, I'd like to make a free resolution of that module. And generally when you try to make a free resolution of a module over a ring, it can go on forever. But if you try to do it over a polynomial ring, then it will terminate, as proven by Hilbert. So that eventually turns into the statement that this map is onto. You can get any sheaf you want by using an exact sequence of vector bundles. So that's the ontoness, if that's something I could explain more about why it should be an isomorphism. But what it means is that we can talk about, we have this basis for K homology. Now, because of the Poincare duality in K theory, we've got a basis for K cohomology, and we can talk about trying to do Schubert calculus in K theory. And we've done all of the geometry necessary to be able to know what the extra term is that we have to subtract off. And the way it gets reported in puzzles is there's this new puzzle piece that looks like this. It's big, okay? And you're not allowed to rotate it. So I've got 4 minutes left to do equivariant cohomology. So I'm not going to do an example of this, but the example I exhort you to work out is this one. So you should do that example. Example, exercise. So equivariant cohomology I really wanted to say a lot about because there's been so much going on this week of restricting equivariant cohomology classes to points, and I might end up going 4 minutes over time because of that. So I'm going to do that. All right, even warned. So in equivariant cohomology. Right, let me say one more thing about equivariant K theory, which was the equivariant analog of this statement. So the theorem, given that cell decomposition, and a torus acting on X preserving cells. So it's no longer true that the classes of the closures of the cells are a basis. So I'm writing it down. This is now the KT equivariant homology of X. But I'm going to be working in cohomology now. Doesn't matter. They're no longer a basis of this because this is just so much larger, as it turns out. They're a basis of this over the KT equivariant homology of a point. So whenever you have, I said this was a functor from schemes to groups, and then in K3 it's going to be a functor from schemes to rings. But actually, because every X has a map to a point, there's always a map back, equivariant map to a point. There's always a map backwards from the K3 of a point back to the K3 of space. Yes? As before, the same. Yes, I'm not generalizing past what I had before. Just like that. So what is this? This is about T equivariant vector bundles on a point. A vector bundle on a point is a vector space. It's about T equivariant vector spaces. This is the representation ring of T, and it's a Laurent polynomial ring. So if you try to compute equivariant K-theory Schubert calculus, you're now going to want to multiply classes of Schubert varieties and expanded Schubert varieties again, but the coefficients you're going to get are not going to be numbers. They're going to be these Laurent polynomials. So equivariant cohomology, even though it's easy enough to work with, it's yucky enough to define that the only thing I'm going to tell you about it in my remaining 0 minutes is this corresponding statement. And the equivariant cohomology of X has such a basis over the ordinary cohomology, over the equivariant cohomology of a point, which is not a Laurent polynomial ring. It's a polynomial ring. And it's a polynomial ring symmetric algebra in the weight lattice of the torus. So this guy is the weight lattice. Now, being a polynomial ring, you expect it to be supercommutative. So, being a cohomology ring, you expect it to be supercommutative. So since I said it's commutative, you should think it must be at all even degree. So my generators here, my weights, are going to be in degree 2. Not in degree 1, like you might think they would ordinarily be in a polynomial ring. If I did that, it should be an exterior algebra instead. So, if I want to do Schubert calculus there, I'm going to need to multiply to Schubert classes, expand in this basis again, and I start getting polynomials in the weights. So I'll tell you what the geometric input is. So before we had this, so non-equivariantly, we had the statement that you can have some subvariety, and you shift it, and you end up with this other subvariety, and they have the same homology class. Equivariantly, the problem is that the way we shift it, so this is going to be some T invariant subvariety defining some T equivariant cohomology class. And there's going to be some other T invariant subscheme defining one. But the way I got from here to here used these unipotent matrices with the identity with little t on them. And every step along the way was not equivariant. It was not a T invariant subvariety. So these are not T equivariantly homologous subvarieties. They're only homologous. So in order to account for that difference, there's this penalty factor that says, what did you have to move through? So you have to add this other term, and the term has to do with how non-invariant those things were. And this bipolynomial ring is going to be z bracket y1 through yn. Let me see what that means. But this is going to be the weight of, remember that I had this family F that mapped down to CP1, and it also mapped to the Grassmannian. This is the weight of how that torus was acting on that CP1. That times the class of the sweep. So you need to prove once and for all that the north pole, if you're rotating CP1, and you have these two fixed points, the north pole and the south pole, you need to prove once and for all they're not equivariantly homologous. But the difference between them is the class of the whole CP1 times the weight. So you get an equation down here that says north pole equals south pole plus weight times the class of CP1. You pull that back to F, push it into the Grassmannian, and it becomes this equation. Where over the north pole you've got this, over the south pole you've got that, over the whole CP1, and then push into here, you have the sweep. And what that does on the puzzle side we need the equivariant piece. So it's like this. It's got zeros and ones in the wrong places, and I like to color it blue. So in my paper with Terry's out, they're always blue. No rotation. And it's going to sit somewhere in the puzzle, in the ij place. And it contributes a factor of yi minus yj. So remember, filling in this, when we have the 1, 0, that was the one case when there was an actual ambiguity in how to fill in those two puzzle pieces. That's the case that this sweep is not the same as x, and you have to keep track of that contribution. And if you change the puzzle path, gamma, to this gamma prime, you turn those 1, 0 here to 0, 1 there, that is what replaces the partial permutation with the 1 for the corresponding sweep. And so that's how we've essentially already done the work to make this thing equivariant. So now when you do Schubert calculus, you don't just count puzzles. Instead, you sum over puzzles. And each puzzle is going to have a bunch of equivariant pieces. And you multiply together the weights on that those pieces are contributing. Add everything together, you get a big polynomial. And those polynomials are the coefficients for the base ring and equivariant cohomology. So final apology, I told you what to do in K-theory. I told you what to do in equivariant cohomology. There is a question, how do you compute Schubert calculus in equivariant K-theory? And I was never doing that. I was computing the classes of Richardson varieties. which is not exactly the same thing. It's good enough, that trick, for computing K-theory and for computing equirate cohomology, but it's not good enough for computing equirate K-theory, Schubert calculus. I can tell you what the class is in a positive way, in the right sense. I can tell you what the class is of a Richardson variety in equirate K-theory, but it doesn't do equirate K-theory Schubert calculus. So, I'm still thinking about that. Thank you.